Hello everyone, good afternoon. So I think you all had a great weekend and now we are back with our, I think this is the third lecture, right? So I got all of your answers for Friday question which I asked you, and the correct answer is obviously the bulk energy and the surface energy, which are the two competing energies which one tries to help in the growth of nucleation of the single crystal and other tries to dissolve it. So today also I will be putting one or maybe two questions during the class, and I hope you will be listening and giving the answer. You can send your answer to my email only, not to HBNI. So this is my email ID, shash, shash, at the rate barc.gov.in. Okay. So just before I start on today's lecture, we will revise what we have done in the last two classes. First one was on the basics of semiconductors. So we thought we learned that what are semiconductors, what leads to the formation of bonds in semiconductors. Then we saw silicon as an example for an elemental semiconductor, doping in silicon like p-type doping, n-type doping. And then we also learned about the compound semiconductor, especially about gallium arsenide and why compound semiconductors are important, how we can be tailoring the different properties in which is easier in case of a compound semiconductor because the band gap can be tailored, and generally the compound semiconductors are direct band gap semiconductors. So because of that, they can be used in optical applications like light emitting diodes, LEDs. And then also they are because their mobility is higher. And what leads to the mobility of a semiconductor being high depending on the EK band diagram? Those things we have studied in the first lecture, right? And in the second lecture, we started with the growth of single crystals, why it is important. Taking in the case of like silicon or any other devices which is dependent on single crystal. So that's why we studied some basis of single crystal, like the theory for the growth of single crystal, nucleation theory, and we also learned about the critical radii, that once a growing nucleus crosses critical radii, then it has got more chances of growth. And below critical radii, because of the surface energies, instabilities are more there. Then what are the factors which are responsible for growth, and what are the factors which are responsible for nucleation? If we have got conditions which are more conducive for nucleation, so we get multiple nucleation. But if the situations are made so that they are conducive for growth, so single crystal growth takes place. And then we learned about the solution growth techniques and vapor growth techniques, right? So now today we will be, and we also started with the melt growth. So when we finished our class on Friday, we were talking about melt growth techniques. So before I go into that, let me know whether everything is clear, I think, till now. And today we will be focusing on the melt growth techniques. And we already have read about the Bernoulli flame fusion, which is used for the growth of Bernoulli method and the growth of sapphire crystals, right? So this we have covered, but just to brush it up, this is the flame fusion. So we are using flame of oxygen and hydrogen. The starting material is Al2O3, which is to make ruby is mixed with chromium oxide. Hmm. And then because of this oxygen and hydrogen, there is a flame formation. That's why it is called flame fusion technique. And drop wise drop alumina drops are formed and they fall on a pedestal here. Very similar here you can see. Okay. and then the single crystal is formed. Okay, so the rate of growth is governed by how much amount of Al2 is falling through this, and thus we can control the nucleation and the growth, both things. And this is happening at 2000 degree, and because the melting point of alumina Al2O3 is around 2000 or 2100 degrees centigrade. Okay, so this we have already read. So Bernoulli method is generally used for the production of ruby and sapphire varieties, and this process involves the melting of powder substance using an oxygen and hydrogen flame. The melt droplet crystallize on a single crystal seed, which grows to produce the crystal ingot. So you will see that in all the melt grown techniques, we generally start with a single crystal seed and on which the crystal growth takes place. So this is a example of homonucleation. You remember yesterday on Friday we have learned there is heteronucleation and homonucleation. So homogeneous nucleation or heterogeneous nucleation. So homogeneous nucleation is like we are growing sapphire crystal on sapphire seed. If you are using something else as a seed or a substrate or something, then it is a heterogeneous nucleation. So mostly in the melt growth technique, we will be using the uh, homogeneous nucleation. Now, this Bernoulli crystal growth technique is known as the genesis of the modern melt growth crystal growth. Why it is so? Like here we will see that this is the first. This is the one. So here what is happening? There is a diameter control growth is there. Just a minute. Just. Mm, yes. So we have read the one all crystal growth technique. So now coming to other technique. So this is the Bridgman technique. This is the vertical Bridgman technique. So how it happens, and this is the horizontal Bridgman technique. So here also what happens, there is a melt, we have a crucible, there is a full crucible is there, and in this the melt is formed. There is a molten material. We put the molten material here, and then the seeding is kept here, or seeding starts from here. And in horizontal Bridgman, the seeding starts from this point, and this is the melt and this is the crystal which is forming. So the temperature gradient within the furnace is made so that there will be a partial solidification and the seed starts to grow. And this is the Zekrolski. Here we will be, this is the full melt, and we will be introducing a seed. And this is the chiropolus in which the seed is touched with the melt. So these all are like modification of the one oil's crystal growth technique by changing the nucleation method. So we will be these three methods, the Bridgman method, the Zekrolski and the chiropolus. I will be talking to you in detail. So the Zekrolski crystal growth, Zekrolski is the name of the Polish scientist. So he started this method. And all the silicon crystal, the semiconductor grade silicon crystal, or even the photovoltaic grade silicon crystal, which we see in the solar panels and all, they are grown by the Zekrolski technique. And this is the most important, technologically important crystal growth technique, which is used world over. So how this technique is there? So first we weigh and mix raw material, and this is loaded in a crucible. So this is the crucible. We have a crucible here, and the raw material is kept in the crucible. So this is the raw material, and then and this is the furnace. These are the coils of the furnace. So using this, and this is some like growth station. This part is called the growth station. The growth station, why we call it growth station? Because this is what uh, uh, maintains your temperature and the gradient and how the solidification has to take place, all those things. So let us go step by step. So we are putting our material, like let us start with silicon only. So initially polycrystalline silicon chunk is there. Silicon is put here, and then using the furnace we are increasing the temperature, and then this silicon is totally melt. This is not there, huh? Initially this part is not there. Okay, so we only have the melt in the crucible. Now this, the silicon melts around 1400 to 1500 degrees centigrade. So this is all at there, and this is the seed crystal. So we have seed crystal. This is also silicon. Now this is initially brought down and it touches the melt here. So the seed crystal touches the melt at this point, and then this is, then translation is started, and this seed is, first we are dipping the seed and then we are translating the seed upwards. So it is called a puller. We are pulling the seed crystal upward, and then slowly this melt start accumulating on the seed and the crystal growth takes place. So this is the crystal. So here, though the temperature here is below this point, this temperature is greater than the melting point, but at this point the temperature has to be less than the melting point. Then only you will get the single crystal growth. So the melt temperature is adjusted so that the first portion grown has a diameter just smaller than that of the seed, and growth has to be there. If this temperature is high, then there will not be any growth. Okay. So, and now because we are growing this crystal, there is no other way of controlling. So this, when the crystal is grown, we have to control the diameter. So generally, if you see the crystal, silicon crystal which is grown is of this shape. So here the seed is there. Then we are growing slowly the diameter is grown, and then, so this part, this is the seed, this is called the shoulder of the growing crystal, and this is the diameter part, and this diameter is controlled, huh? So how we are controlling the diameter? And when we come to silicon crystal growth, which is used in your, so I told you first day also, generally the diameter of this crystal is around say 6 inches diameter to 12 inches diameter. So 12 inches diameter means 1 feet. So you can imagine the size of the crystal, huh? So it is around this much diameter crystal is grown using the Zekrowski technique. So the question is how we are maintaining the diameter of the crystal, and the length of the crystal is even 3 meter. So I will be showing you few video clips where you can see, but how it is maintained. Actually, I will just ask that now I start the class at 2:30, so it is better if you all join it by 2:30, 2:31 or something like that. Because some people are still now joining, so it disrupts everything, and then so you just make your schedule like that. So first, before going ahead, what are the advantages of Zekrowski? It can grow very large size crystal and better control over nucleation, shape and growth rates. So nucleation is controlled by the seed. And shape and growth rate, we will be seeing that it is dependent on the pulling rate, and it is also dependent on the temperature of the melt. So what exactly is happening? I told you that melt temperature is greater than melting point. But if say melting point is say 1404, so it is not like melt temperature is you are keeping it at 1500 degrees centigrade. It is also melt temperature can be, but if it is so high, there won't be any growth. So it is just melt temperature is very slightly higher than the melting point. So maybe at 10 degree. So, and how much is the actual difference between the melt temperature and the melting point? It decides the diameter of the growth. Okay, and then coming to the disadvantages of this method is like melting point can be very high. So this like not only silicon, we can grow sapphire, ruby, and a lot of technologically important materials are grown. Nd:YAG crystal is grown. So these material all have got a melting point of around 2000, 2500 degree. So those temperature can be achieved using the Zekrolski. And we can have because we are going to so high temperature, so we may require vacuum. So or there will be, because the growth is at happening at very high temperature, so there will be thermal stresses inside, and there can be constituent evaporation occurring, or some material can evaporate. So this constituent evaporation occurs, we will be seeing this in the case of gallium arsenide. So I will be coming to that. And then we have a contamination coming from the crucible, because we are holding the melt in the crucible, temperature is very high. So these are all the disadvantages. Now coming to how we are controlling the diameter. So
Ma'am,
yes,
I have a question.
yeah, sure.
You had said that we need to be very close to the melting point for
Hmm.
the crystal growth to be efficient.
Yes.
Does this pertain to the same principle that we had discussed in the last class regarding the crystal
Obviously,
formation to be near
obviously, these
the
are about
equilibrium point?
nucleation. Yeah. So we are not at the thermodynamic equilibrium, right? So that we have read that crystal cannot grow at thermodynamic equilibrium. So it is near the thermodynamic equilibrium, right?
So
So
near the melting point is the near to equilibrium point as well.
yeah, at the melting point, it is equilibrium. So what happens at the melting point, if your seed is touching to at the melting point on and the melt both, so there will not be any crystal growth. For the crystal growth, and the seed has to be at a lesser temperature, and melt has to be at a slightly higher temperature. Okay. So
Okay.
yes. Okay, so now coming to how the diameter is controlled. So when this growth is happening, the single crystal growth is happening, so we don't see anything, and we are not like seeing the diameter and controlling the growth. It is not by manual. Only the only signal which we get from the growing crystal is the weight of the crystal which is happening. Huh? So we have the seed. Okay, we have this seed, and we know the growth of this weight of this seed. So say it is say 10 grams, or even less than that, 1 gram or something. Now it is coming and touching our melt. So this is the melt. Let us, we are taking the case of silicon only. This will come and touch here like this. Okay, now we are pulling this seed very slowly. So some silicon from this melt will get attached to your seed. So there will be a change in the weight signal. So we are only able to get input on the weight of the crystal. No other input is coming. And we are using softwares. software are using, which is called the automatic diameter control software. So this is called the ADC software. ADC software. What does ADC means? A means automatic, D means a diameter, and C is the control. Okay. So this automatic diameter control software, what it is does, initially when we are going to start the growth, we tell the software that I want to grow so and so crystal, like I want to grow a silicon crystal, which should have a shoulder region, say this to this is say 10 centimeter. And here the diameter is say 12 inch. Then there will be like 1 meter length of 12 inch, and then I will be terminating. So this is 12. And I know the density of my silicon and I know the geometry. So at every given point of my growth, I know what will be the weight of my growing crystal. So this. So initially when it is in this shoulder region, what will be at every layer? Theoretically, I know what should be the weight of the growing crystal at every point. Okay, the computer will, your software will calculate that. So from that, what we do, then we calculate the growth rate and calculate error. Now, what is this? This is theoretically it is calculated at every given point. What should be the weight of my crystal? And then when the crystal is actually growing, we are getting the weight of the crystal. Okay, so this is experimental value, and from here we have got the theoretical value. Okay, these two values are compared at each and every point, and from this we calculate the error, means whether the actual weight of my crystal is more than what it should be at that given time or less. If my crystal weight of my crystal is more, that means whatever it should be growing at that given particular, it has grown more. So what it will do, my software, what it will do, it will give power signal to the power supply. Power supply will increase the power so that the temperature increases of the melt very slightly. It will be like 0.1 degree. So if my melt temperature increases, the growth rate will decrease. Okay, so growth rate will decrease means it will try to match my theoretical value, because my experimental value was more than the theoretical value. So there was an error because of that, and the temperature increased. If my theoretical value is more than the actual what is happening, so it will decrease the temperature. Very less decrease, but it will decrease so that the growth rate increases. So we see decreasing the melt temperature increases the crystal diameter and vice versa. Also, this is the main control, but also the increasing the rate of pull or the relative rate of rotation. Okay, in this case, the crystal is also rotated in the melt. The seed, no, whatever is coming and touching, not only it is being pulled up, it is also rotated. Why it is rotated? Generally, the rotation is to homogenize the melt and homogenize the temperature gradient within the melt. So, rate of pull, increasing the rate of pull or the relative rate of rotation of the crystal decreases the diameter. The rotation and pulling rate used are depend on the material being grown. So generally, like for silicon, which has got very good thermal conductivity, and so they are grown very fast, because you have to conduct the heat. So because your melt temperature is more than the melting point, and you are solidifying your material. So you have to conduct that heat, and it has to come down to low temperature. So material which has got good thermal conductivity and also good crystal properties, that there are cracking and lot of issues are there when you are growing a crystal. But just to give you a very brief idea, so it depends on that. So silicon or even metal crystals like copper and all, we can grow very fast. But when we come to oxides, like sapphire is there, I was talking about yak crystal, or similar to that, many other like molybdates are there, borates are there. So their thermal conductivity is very low. So their pulling rate has to be very less. So, like in case of silicon or germanium, we use a pulling rate of say even like 10 millimeter per hour. It is not very fast also, 10 per hour. Whereas in case of this is like silicon or germanium. Whereas in case of oxide, we are using 0.01 millimeter per hour. So that's why crystal growth is a very slow process. And depending on material to material, we have to change it. So, and when we are going to large size crystals, so we need slower pulling and rotation, because we have to homogenize the melt. There should not be temperature when like this layer is growing, say this layer is growing. So within this layer, from this to this, there should not be any temperature gradient. And whatever the whole layer which is growing should be in thermodynamic equilibrium. So all these points has to be taken, otherwise there will be dislocations or some other defects will come and you will not get a good single crystal. So these are just like the very broad parameters. So if I can round up whatever we have learned. So material to be grown is melted in a suitable container, so which is called the crucible. The crystal seed of material to be grown is placed in contact with the surface of the melt. Temperature of the melt is held just above the melting point. Highest viscosity, low vapor pressure favors crystal growth. So whichever material has high viscosity, because high viscosity, why? Because it will start to get attached to your seed. Then the seed is gradually pulled out of the melt, and the melt solidifies on the surface of the seed. So that is how your crystal growth takes place. The melt and seed usually rotates counterclockwise. Means if my this is my seed, so if I am rotating my seed in this, so but this is not always like this crucible will rotate in this direction to maintain a constant temperature and facilitate uniformity in the melt. But this rotating the crucible, this crucible rotation is generally used when we are growing very large crystals. But generally in lab size systems, only the seed is rotated. And this leads to the growth of very high quality crystal and less defects. And because this whole growth can is taken inside a is happen inside a chamber, this is called the Zekrolsky crystal growth chamber. So we can have inert atmosphere, or we can use pressure around growing crystal, or to prevent material loss, like or oxidation, nitration. We can use uh, like we can use hydrogen, or we can so or nitrogen. So different kind of atmosphere can be used. Even in case of silicon growth, so phosphine, like to dope it with phosphorus or boron, so gases are used. So you can change the environment in the crystal growth system, so that the effect, whatever kind of effect you want, you if you are growing an oxide crystal, you can have an oxygen environment. If you are using a semiconductor, you can have an inert environment, or you can have a reducing environment. So these are the flexibilities you have when you are growing by the Zekrolsky. So this is the chamber. You can see this is the actual in the lab photograph I am showing. This is the crystal growth Zekrolsky. The this is the crucible here. You can see this is the crucible, which so here in this case it is a quartz crucible. This is the furnace. and this is the growing crystal. Okay, so this all is happening here inside this. This is the load cell. It is called load cell. What is does it is the weighing, this is which is taking the weight of the growing crystal at every time. And the seed, this, and with the load cell, the seed rod is there. So this seed comes. So here you can see in this video, from the top I am showing this. So this is the furnace, this is my crucible, and this is the seed. Okay, and this part is the crystal which has grown. Okay, this all is the melt, this is molten at the given time. Okay, and this seed is connected here. Okay, so this is actual lab photograph of single crystal growth. And this is for the germanium. So we were, germanium is another semiconductor. If you remember, the semiconductor story started with the germanium crystal. And so we have, so this is the crystal after the growth. So it started with here, and then we have got this length is 150 mm and diameter is 2 inches. So so this is actual video. So you can see here, these are the polycrystalline chunks, and some part has already gone molten and some are still polycrystalline. And this is the seed. You can see seed has come, and if you see properly, it is rotating. Can you see it is rotating? From here you can see, and it is touching the melt. Now it has already touched the melt, this point. So crystal is growing from at this point. So keep watching. So this is actually Zekrolsky crystal growth happening. So this from this seed, initially we have decreased the diameter and crystal will be happening. Now you can see, sorry, this one. Okay, is it visible to everyone?
Yes, ma'am. Yes, ma'am.
So you can see now that seed was there, it is still here, and now this shoulder has come up. Okay, this is the shoulder part. Okay, and how it goes. So basically this is a time elapsed, so you are seeing at different point. So you can see here it is rotating, and this is the crystal growing. This all is molten. This is inside the crucible. This is the crystal which is growing, this part. Okay, this you can see. So this is the crystal. This is the diameter. This is growing. This is the seed, and this is the shoulder. Okay. And now you can see that crystal has grown. This is the growing crystal. So it has become quite big. Okay. So that is how the crystal is grown in the Zekrolsky. Now I will be showing, this is, that was a lab photograph, what a lab video. And that full crystal was grown in around 14-15 hours. So it is not like just the small video clip I have shown you. It is not so simple. So the full growth of that crystal which I have shown you, so it takes around 15-16 hours to grow the full crystal. And before that also you have to do lot of loading the material, creating vacuum and all those things. So full takes around, and then cooling and then taking out. So it takes around 3 days for one single crystal growth for a germanium of that size. And then when we go to oxide crystal, even a smaller size than that, it takes around 1 week or maybe 2 weeks. So here I will be showing you silicon crystal growth, which has been taken from internet, just to show the like industry how it is happening. Silicon growth in the industry by the Zekrowski technique. So it is not very clear, but you can have a, so making silicon crystal, huh? The animation is there. So this seed crystal is coming, it is touching the melt. You can see here, this animation is there. So here the seed crystal is rotating in this direction and the melt is rotating in the opposite direction. And our seed is being pulled out, and this is the crystal which is growing. Okay. Now this is coming up. You can see this is molten ultra pure silicon, because when we are growing using this silicon in the industry, your ICs, your phone, your mobile, so it has to be very pure, and the typical wafer diameter is 4 to 12 inch, as I was saying. So nowadays in the industry, 12-inch diameter, that is 1 feet. So that kind of diameter of this silicon crystal is taken place, growth. And this length is in meters. So you will see here. So it is being taken out. So crystal is growing, till now growing. It takes up around 48 hours to complete the growth. You are able to see it properly?
Yes, ma'am.
Okay, good. Hmm. So it is there. So now it is an actual. I will be showing the video from the actual crystal growth, happening in the industry. So this is the seed crystal. What you saw that it was a lab footage. Now is, so this is the crystal. It is a very big. This crystal is from
Hello,
this. Yes.
ma'am.
Yes.
Yeah, whatever you are, we are taking the melt, that is the pure crystalline form, or it is the some
I think
impure,
let.
the material for melt.
Uh, yes. Yes.
Yeah.
I'm not getting your question. What you are asking?
जो whatever the material for melt, it is the
Yes.
material of the crystal grown or some other material.
Yeah, you have to take the same material to grow. That is what the melt growth technique
Its
is,
its
right?
purity, its purity will be what? The
Same
purity of
purity.
melt.
Whatever you want to grow, you have to use the same purity, right? Now,
Okay,
there
from
is
that
no
we have to.
purification happening during crystal growth. There may be very little because there is some segregation and all happening, but generally you have to take the same purity and
It is the
same material.
purifying process. Actually,
Pardon?
crystal growth is the purifying.
It
Crystal
is
growth is the
pure.
more purifying. Huh.
It is a purifying process. In that way, you can say that there is a segregation coefficient for all impurities. So, whatever you are putting there in the melt, some will get solidified and some will be left in the melt. But if you are using, like you are going, like in the case of silicon, that kind of purity you're saying, so you cannot start with a very low purity and think that I will get a very high pure single crystal. The purification of one order maximum, even not one order purification, you can get using a single crystal growth. some
Okay,
some
okay.
very small amount of purification will be there. Also it depends on the kind of dopants are there. Now so when if any impurity or dopant which has got good segregation coefficient, they remain dissolved in the melt and you get pure
Oh,
solid. But there can be
okay,
some impurities which has got similar tendency or similar dissolving coefficient in the solid phase and in the liquid phase. So those things you cannot purify using the crystal growth. Okay.
okay, okay, madam. Okay,
Okay.
thank you.
So I will come back again to this no, because you must not have seen everyone. So this was there. Hmm? So this is the actual which is growing, that crystal was growing. We will see this again because that question came up. So this is the seed and now this is the crystal which is growing. So this diameter was there. This we are seeing from outside, huh? So this is the crystal which is growing. And can you see the size?
Yeah, madam. Seeing.
Note the length of the crystal. So a human is very small, huh? This is around 3 meter or 4 meter, and this is actual industry footage. So this is like the level of single crystal growth technology generally Zekrolski in the current industry. So this is for silicon. Now this is the crystal. But when you are going for the making of ICs, chips, which is used inside your mobile or anywhere inside your computer, your laptop, or even in our satellite or whatever, huh? Any technology you think about. So this ingot, this is called the ingot, silicon crystal ingot, which we are growing from the crystal growth. But this is not used directly. We have to cut and polish it and then wafer it. So first this crystal is there, then we are wafer slicing and polishing. So you can see here, this is the crystal, huh? It is not very clear, but this is slicing, huh? Slicing is happening here. Okay, so there is a blade and now you can see the slice. This is the slice and okay. So this is the wafer. This is your silicon wafer. And then this whole thing, this slicing of wafers, then they are polished and then your IC deposition is there. Your this is whatever kind of ICs are fabricated, all these things. So this is all done by robotic. Minimum human interventions are used in this, and this is like conveyor belts are there. Then the full process is carried inside a clean room such that you give the command and your ICs come out. So if you must have seen those videos for Intel and how it is done there. So this is the full silicon growth industry, silicon crystal industry, from polycrystalline material to crystal growth to the IC fabrication. So semiconductor industry as you call it. Okay. So this is the Zekrolski part. Now silicon we were talking about till now, but what about the other semiconductor, our compound semiconductor? So gallium arsenide. Now coming to gallium arsenide, it is also grown by the Zekrolski technique, but there is a problem here. We have got gallium and we have got arsenic. Now it is more difficult to grow than silicon. Why it is so? And because of this problem, we will be modifying the Zekrolski method. So the vapor pressure, so at 1238 degree, which is the melting point of this material, the vapor pressure of arsenic is around 10 atmosphere, while gallium is only 0.001 atmosphere. So arsenic has got very high vapor pressure. So because of that, it will start evaporating. So arsenic is rapidly lost to evaporation, resulting in gallium rich melt. So in case of silicon, that problem was not there, but now if we are like taking it to the melting point, so there will be like we will not have gallium arsenide remaining, we will have gallium more and arsenic less. So we will not be able to grow the proper semiconductor. So what we are doing, we are just making small changes. So we are putting a cap to encapsulate the melt and stop the partial evaporation. So in the disadvantages of the Zekrolski technique, you have said that there can be partial evaporation. So this partial evaporation example we are seeing now. So this cap is typically of boron oxide, which that melts at 400 degrees. So boron oxide will melt initially. So here you can see, so we have got, this is the boron oxide melt. So boron, this is our melt of gallium arsenic, Ga. This melt is there, but here, from here onwards, this boron oxide melt is there. So our gallium arsenide is never able to come to the vapor with the atmosphere and get evaporated. So there will be an encapsulation of boron oxide at every time. So a layer of molten inert boron oxide spreads on top of the molten feed material, preventing preferential volatilization of the more volatile arsenic. This allows the seed crystal to be lowered through the liquid cap and pulled out of the cap. So once it is inside, the growth is happening inside, then we can, once it comes out, there is no problem because it is in the solid form. So this is a modified Zekrolsky method. So though Zekrolsky method is bit sophisticated, but at the same time it gives lot of leverages. You can do lot of tweakings, lot of value additions to go for one material to another material. So that is how the Zekrolsky growth of gallium arsenide happens. So here I will take 1 minute of break, and then we will come back and go for the other growth techniques. Okay, so just 1 minute of break. Okay, you have all understood the Zekrolski method, I hope. I know it is not very easy to understand or visualize. That's why I tried to put those video clips to just have you can imagine how it is happening and all. And you can get back to me, mail me if you want to know better or if you are more interested in that technique. And now we will come to the Bridgman method, which is the another melt growth method and also used commercially for the growth of many materials, like halides are there, sodium iodide, cesium iodide, all those things. We will come to this. So in the Bridgman method, what happens, the growth is happening inside a crucible. In the case of the Zekrolski, we saw that the material, molten material, is taken inside the crucible, but here the growth is also happening inside the crucible. So the crucible size, here you can see this crucible is like this and there is a very sharp tip. This is the full crucible, and initially the full material is taken inside the crucible, the raw material, and now it is put inside a furnace. So this is the Bridgman furnace, and a Bridgman furnace has got two zones. Two zones means two temperature zone. So in this case, you can see that there is one zone here and the other zone is here. So this is zone 1 and this is zone 2. What is the difference between these two zones? In zone 1, you can see this furnace coils are there. No? They are very closely packed. That means the temperature of the zone 1 is very high. So this is the hot zone and this is the cold zone. So at the hot zone, temperature is higher than the melting point. Here the temperature can be higher, means you can even keep it at a higher temperature of say 10 degree to 50 degree higher than the melting point, so that initially when you are loading the crucible is loaded here up to here only, and the full material is molten, and then slowly the crucible is lowered, and this cold zone is at a temperature much less than the, so temperature is much less than the melting point. Say this is around 100 degrees, so melting point minus 100 degree, melting point minus 100 degrees. So this is the cold zone, so this part, and initially we keep our crucible here, the material gets molten, and then slowly we are lowering in this case. In earlier case we were pulling it, now we are lowering it. So this, so here the temperature is high. So this is this temperature, if we are plotting temperature in this zone. So temperature is high. This is our melting point. And here the temperature is low at this point. So as my crucible gets lowered, my crystal growth takes place here. So we have got two isothermal zones separated by a adiabatic zone. So this middle zone is called the adiabatic zone. The nucleation starts at the tip of the crucible. So that is why this specific formation is there. So the tip of the crucible is very thin, so that this nucleation starts here. This becomes the nucleation point, and we seal the crucible in the ampule, this is, and then melt, and then the crystal growth by passing the ampule through the temperature gradient zone. So I will show this video here. This is from, so this is from net only, you can also find out. So this is for educational purpose. So just, so we have a furnace in which the growth is happening. So this is just the furnace is there. So you see this is how, let me. So this is the crucible. So crucible can be like here in this case it is an alumina crucible, or we can have a quartz crucible, we can have a platinum crucible, but basically this tip is important because the crystal starts growing from this tip, and then this tip is there, So now this is our furnace. This is the Bridgman furnace. We have the hot zone, we have the cold zone, and here we want at in this is the adiabatic zone. Because why adiabatic? Because we are not providing any energy to it. Huh? And here this temperature is above the melting temperature, this is below the melting. And somewhere here there will be a temperature gradient. If I am plotting temperature here, so in this, if I, this is the height of this and this is the temperature x-axis. So temperature is decreasing here and somewhere here the this part will start solidifying and the crystal will start growing. It is coming down, coming down, coming down, and it's coming down. Okay. Okay, so you see the crystal has started growing. Oh, can you see it? So at the tip, the crystal is growing. Now crystal is growing. As it coming down, larger. Okay. So this way, this is in the melt form and this is in the crystal form. So we have got the crystal and the melt both existing. This is at a cold zone and this is at the hot zone. So we have got so as it comes into the cold zone, the full crystal growth is, crystal grows. So this is called the the Bridgman crystal growth technique. So the advantage is these growth stations are very less expensive because we are just putting two temperatures. So coil temperature is different. We can change the temperature by just giving a different currents at the top and the lower coil, and just we are just lowering it. The lowering rate depends on the material which we are growing. It can be very fast, like 1 mm per hour to zero point 0.1 or 0.01, or even high can be 10 mm per hour. But still, if you think 10 mm per hour, that is 1 centimeter in 1 hour. That is the lowering rate. Or it can be 1 mm, or it can be 0.5 or even 0.1. So the sealed ampules permit growth of hygroscopic material, like material which gets are getting absorbs water or moisture very easily, like sodium iodide is there. So hygroscopic material can be sealed inside. So temperature gradients are small, so the crystal have less thermal stress. But what are the disadvantages? That is difficult to retrieve the grown crystal because there is a crucible. So crystal is growing within the crucible, and lesser control over nucleation because no, nucleation is happening only at the tip. So you are not able to control it can happen that there are multiple nucleation happening. So there are methods of changing this tip, making it into different shapes, or in some crucibles, what they do, they put a seed here, seed of the same material here. So this is the same material which is put here, and then the crystal grows from here. But then you have to make the furnace also so that the seed does not melt. And low temperature gradient is there, so there can be like glass form can also be there. Now we come to the chiropolis. So in case of a chiropolis, what we are doing, we are growing like that. We are just dipping the seed, this is the seed, in the melt, and this is the melt, and we are not pulling or lowering, we are just letting it remain there, and we are slowly decreasing the temperature so that with the seed the whole crystal grows. The Chiropolis method uses a seed crystal that is dipped into the melt. This is more easier and you can grow very big crystals. This is crystal. You can see this man is sitting here and this is the crystal. So these are like sapphire crystals are there and used for our mobile glasses and all. So these are like Gorilla Glass and whatever we are using the word. So they are generally sapphire crystals used for very good mobile glass and display glasses. So they are grown by the Chiropoulos technique. So growth is maintained by continuously lowering the crucible temperature. So the full crucible's temperature is lowered so that this nucleation is there, and slowly the melt gets nucleated, and so the linear growth rates are low, but the area of the growth phase is large, so that volume growth rates are reasonable. So the whole this phase will be growing together. So Chiropoulos method is widely used to produce halide crystals for optical components and all those things. So this is also used in industry. And now coming to the float zone method, floating zone method. So here what we are doing, the basic idea in float zone method is crystal is growth is to move a liquid zone through the material. So here we have, if properly seeded, a single crystal may result. So we have, here you can see this is the crystal, and this is the polycrystalline part. So initially what happens, we have to make a rod of the material, and a very small zone is melted. Here you can see from here, only very small zone is melted at a given time, and then this zone is translated, taken above. Means the crystal growth happens here, and the polycrystalline, in this case, like we can bring it down. So this part is now molten, this is liquid, this is your crystal. Now if I now take the next, I take this. So this polycrystalline will get dissolved, will melt, and this part will solidify. So because single crystal seed is there, crystal is there, so this will be forming the crystal, and my polycrystal part is getting into the melt form, and then it is going into the crystal. But the advantage, but in this case what happens, the size of the crystal growth is very small. Generally whenever it is grown, it is used for the growth of very small crystals, like grown crystal is around 20 mm, means around 2 centimeters. But when you are doing making crystals for some research purpose, or you just want to find out their magnetic properties or something like that, so very small crystals are good enough. It is also used for the growth of alloys, metals. And this heating arrangement here can be done by two methods. One is like this induction coil, which you can see here. The other is by using xenon lamps. So that then it is called the optical float zone method. So optical heating is there, or RF heating. So this is the two kinds of heating which is used for the float zone method. And but we cannot use this for those material for which surface tension, gravity and surface tension are the only thing which is there. So if the surface tension of the melt of the material is not good, then what happens, this molten portion is there, right? So if it is molten and it is not held by this and this part, if the surface tension is not good, then it will drop down because of the gravity. So you cannot produce this material, those material for which the surface tension is bad. So the advantage of this material is that the molten material is only in contact with its own solid and in vapor phase. So it does not contain any harmful impurities. So silicon, when anyone is growing very high purity silicon, like no, for detector grade silicon. So it is grown using the RF float zone technique. So, but the method has obviously desirable features for the growth of crystal of many reactive material, but the only large scale use is for silicon. So silicon, very high purity silicon, oxygen free silicon can be grown by the floating zone method. So it has also industrial application. But in many labs, in many research institute, we will see the optical float zone method for the growth of very small size single crystal, which is used for the research purpose. So this is an example. So this is the optical float zone method. So we have this this is the xenon lamp, this is the xenon lamp, and we have got the halogen lamp is there, and we have got ellipsoidal mirror. So what this ellipsoidal mirror does, it focuses the energy to a very small zone. So that is the floating zone. So this is why it is called floating zone, because it is between, this is the feed rod, means this is the polycrystalline, and this is the crystal which is forming. It can be on any side, huh? We can have the polycrystalline top, or we can have the polycrystalline on the lower side, depending on your machine. So the crystal is growing here. This is the crystal growth part, and this is the feed rod. Feed rod is the polycrystalline part. And this, if this is the feed rod, so our zone will be moving on the upper side, and this, and the crystal is forming lower. And we can also put a seed rod, and we can and this is the actual photograph of the system. So these are the mirror, there is a zone, and the crystal is put in between. So this is the, this, with this we come to the end of the single crystal growth part. And now only single crystals are not important, technological important material which is used for devices and all. Thin films are also important. So there are many devices which are based on thin films, like our like gas sensors are there, squid is there. So thin films are, this optical thin films are there. So we will be just learning about the thin film deposition technique. So before that, today's question was that, my question was, which you have to answer by today evening, is that why we gallium arsenide cannot be grown by normal Zekrowski technique, why we have to do some modification in the Zekrowski technique, and what is the modification. Okay. So question is like that. First part of the question is like, why we cannot grow gallium arsenide by normal Zekrowski technique, and what is the modification in the Zekrowski technique we have to do to grow it. Okay. Got the question, everyone?
Ma'am, can you please write the question in the chat box, because this is a little bit longer than the question yesterday last
I
time.
will tell again, just here. We have learned about the growth of gallium arsenide, crystal growth, right? So why it cannot be grown by normal Zekrowski technique, and what is the modification we have to do for its growth? What modification we have to do for the growth of the gallium arsenide using the Zekrowski technique? Okay, right, everyone? And please send your mail to this is my email ID, shash @brc.gov.in. Now we come to the thin film deposition. Okay, before going into that, if I will just will briefly, this is the part which I was covering. I am supposed to cover. Photovoltaics is there, thermoelectric is there, but I have started from the device worthy materials, because I thought it is better. So we have done the importance of fundamentals of semiconductor, then important elemental and compound semiconductors, germanium, silicon, 2, 4, 3, 5, 4, 6 amorphous silicon, single crystal growth technique we have done till now, growth of silicon, growth of gallium arsenide, production of silicon wafers, and now we are going for the thin film deposition technique. So similar to the growth of single crystal, also surface energy and the interfacial energy are the two important things which leads to the growth of a thin film. So before going, in case of thin film, okay, I will, before I end, I will give what is the question again. I will repeat the question again before the end of my lecture today. So the film growth in terms of surface energy can be described by the energy of the grown film, this is the energy of the substrate, and this is the interface. So layer by layer growth, the surface energy of the growing film must be less than or equal to the surface energy of the substrate minus the interfacial energy of the film and the substrate. So if this is the energy, this is the surface energy of the substrate and this is the interface, so the subtraction, so the energy of the film should be more favorable, then only the film will grow. Means your energy of the film, the surface energy of the film should be less, then only your system will favor the growth of the film. So interfacial energy, how you describe it? It is the excess energy at the boundary between the film and the substrate or surrounding material. So it represents the energy costing to form that interface, and it is crucial for adhesion, nucleation, and film structure. So lower interfacial energy makes forming new nuclei easier. So how does the like we have seen the crystal growth. So similarly, how the thin film grows. So similar, very similar. So there are three techniques by which the thin film growth happens on a substrate. So we have a substrate and we are thin film is growing. So it can be layer by layer growth, it can be island growth, or it can be layer plus island growth. So layer by layer growth is also known as Frank van der Merwe mode. So in this case, the film grows with only the surface layer having fractional coverage at any instant. Thus, the interface width at the film vacuum layer is one atomic layer. Okay. So initially there will be one layer, full formation of one layer, and then there will be formation of the second layer. So there will be always one atomic layer coverage of the film, of initially the substrate and then the film which is growing. So one atomic layer coverage will be there. Now coming to the island growth mode, it is also known as the Volmer-Weber mode. So the film does not wet the surface. Wet means it does not make one full layer. So one full layer is not happening here, so it is making islands kind of thing. So the film does not wet the surface and the bower condition is not met. The interface width of the growing surface increases with time. So initially we have this is there formation, and then slowly it is increasing. So we have got formation of islands on the substrate. And the third mode of growth is the mixture of both of this is the layer and the island growth. So it is known as the Stansky-Kastranov mode. The film during growth, after wetting the surface, the thin film grows in an island mode and the interface width increases with time. Okay, so there will be this, there at some position the thickness of the film is less and at some position it is more. So these are the three types of the thin film growth models. Now, why are thin films important? So film is basically a layer of material ranging from fractions of a nanometer like monolayer to several micrometer in thickness. Thin film, so we have got this, it can be micron, it can be 100 nanometer, or it can be even 1 nanometer. So where we have got like just 2 atoms or 3 atoms, or even one monolayer. When we are using the word one monolayer means one layer of atoms are there. So thin film technology is based on three foundation, that is fabrication, characterization, and application. So fabrication is thin film deposition, which we will be covering in this lecture. And characterization, you have learned already few of the characterization techniques. And applications, one of them will be the like the photovoltaic. So thin films are basically two-dimensional systems and are of great importance to many real-world problems. Their material costs are very small. So now, till now, we were learning about the silicon growth or the single crystal growth. So here, there you have seen like very huge material, very huge, volume is there. But in thin films, we have got the material used is very less. So that's why the material cost is very small as compared to bulk material, and they perform better in many places. They perform better when it comes to basically surface processes. So just I will take 1 minute break, and then we will carry on. Why thin films and others. Okay. Hmm. So we have been till now studying about the bulk material. So they have got their fixed properties, and depending on their application, they have got many applications are there. But when we reduce the size, when the thickness is reduced beyond certain limits, so there will be some changes, and this is called the size effect. And because of that, thin films has got many attractive properties are there, and it can be tailored. So devices with thin film, they occupy less space, their fabrication is easy, so they are therefore inexpensive and all. So thin film growth techniques can be divided into two different ways. So one is the physical vapor deposition technique, and other is the chemical vapor. So as the name suggests, physical vapor deposition is there is whatever material film you want to deposit, you are like physically transporting them. The vapor is there, and then you are depositing it on a substrate. And in case of a chemical vapor deposition, there is some chemical reaction which is happening. So you are not exactly taking the same reactor, same material on of which you want to grow the film. You are taking some reactants which have some reaction, some chemical reaction is there, and then you are getting the film. So we will start with the physical vapor deposition and then come to the chemical vapor deposition. So physical vapor deposition is a purely physical process, and generally high temperature and vacuum evaporation is there. And in case of thermal vapor deposition, we have got the basic steps are like, we can have a deposition. So there can be, we are evaporating material. So there is a source, and this is the substrate, and this is the source, and we will be evaporating the material. And because it is just physical vapor deposition, so material gets evaporated and then it sits on the substrate. So how we can evaporate? We can evaporate using thermal evaporation, or we can heat it by electron beam, or a molecular beam we can form, or we can use laser, or we can use sputtering. And then the evaporant, from here the source, they evaporate, they transport, and then they condensate on the substrate. So this is basically the process of thin film deposition by the physical vapor deposition. Now coming to the first one is the thermal evaporation. So what happens in the thermal evaporation? So as the name suggests, we are thermally heating the material and evaporating it. So we have a, here it is a, you can see this is the system full there, and this is the material which we want to evaporate, and this is the substrate wafer we have taken here. So this is the substrate on which we want to do. So this is hold on the top of the material, molten material, which, and it is heated inside a crucible. Here also crucible is there, but it is not similar to what we were seeing in case of single crystal growth, because here the material is very less. So we can have a wire like like tungsten, molybdenum, very high temperature material are there. So we can have a wire is there, or a foiled boat is there, or alumina coated boat is there, or wire. So we put this material here, or we can put a wire of the material which we want to evaporate inside this wire helix or somewhere, or we put a alumina crucible and then heat it, so in a tantalum box. So this goes here, and then we have a vacuum enclosure. Now point comes is that why we require vacuum. So whenever we are growing a thin film, we require vacuum because we are evaporating it. Now if vacuum is not there, then what happens? Whatever is getting evaporated, it will collide with the our air molecules, and then uh, they will not be able to travel to the substrate. So that's why vacuum is very important in all thin film growth techniques. So metal to be deposited is placed in an inert crucible. Sorry. Chamber is evacuated to a pressure of 10 to the -6 to -7 torr. The crucible is heated using a tungsten filament. So we put some current is flown here, pass through the crucible, or an electron beam to flash over it. Just give me 1 second. No? Just okay, sorry. So I was talking about the vacuum. So why do we need this kind of vacuum at 10 power -6 to -7? We need a vacuum pump and all those things, because the evaporating material, the atoms or the molecules which are getting evaporated, the before they should be reaching the substrate before collision. So their mean distance which they travel should be more. So that's why we require a vacuum. So here you can see a typical thermal evaporation system. You all must be having that in your lab also. This is the very basic for making any thin film. So here we have the substrate is kept here. This you can see here. The substrate is, and these electrodes are there. So we keep the material which we want to evaporate on this electrodes, and this goes to a vacuum pump down, and current is flown across the electrodes. So this is resistance heated evaporation. So it is simple, robust, and in widespread use. but it can use go to a temperature around 1800 or around 1000. And the coil which we use is generally tungsten, tantalum, or molybdenum, because they are inert at this temperature, and the current which flows across is around 200 to 300. So we are going to pass very high current to evaporate our material. And because of this very high current, so there will be some IR radiation will be there, but that generally do not harm the grown films. The deposition rates are around 1 to 20 angstrom per second. The rate of deposition means how much material is getting deposited on the substrate. It can be controlled by the current which is flowing through the electrode. So if you want a low deposition rate, we have to pass low current, and we can have a thickness monitor inside this. So there will be a thickness monitor, that is generally a C-cut quartz crystal, and it vibrates, and it has got vibrates with some given frequency, and depending on the mass which is getting deposited there, it gives like it will give you a value of the thickness of the film which is getting deposited, and depending on that we can change the current which is passing. So that's how we can also regulate the growth rate or the deposition rate. And common materials which are evaporated is like gold, silver, aluminium, tin, chromium, antimony, germanium, indium, magnesium, gallium, or like cadmium sulfide, lead sulfide. So a lot of things are there, calcium fluoride, lots of system can be, and the system can be upgraded for multi-layer deposition. Means multi-layer means one layer of one material and second layer of, so two multi-layer, or you can have a sandwich structure. So how to go for multi-layer? We have got two sets of this electrodes. So we have got here only two electrodes, but if we get two more electrodes here, so like we are passing current at one time through these two electrodes, and at one given time passing current through the other electrode. So in that way we can have a multi-layer. So, and we are using this, like now for why we are using tungsten, tantalum, molybdenum, we can see their melting point is very high. Now for the tungsten, tantalum, molybdenum, it is going around 3000 degree. So it is, so we are using, but for the crucible, but we can also use graphite or boron nitride or alumina. So no, these are the crucibles, but we cannot pass current directly through these like alumina or boron nitride. We have to put this crucible inside any coil. But this is a very versatile technique, and generally most of the research lab have a thermal evaporation system. Now coming to the electron beam evaporation. So there are
Ma'am, I have a
yes,
question about
yes,
the previous one.
yeah, yeah.
Uh,
Tell,
d-
yes,
does the
yes.
thin film retain the crystal structure of the target material, or does it adjust itself to the substrate?
Obviously, it adjusts to the substrate. The target has nothing to do with the thin film which you get ultimately. So because it is evaporating and it is taking the shape of the whatever substrate you are depending on, and kind of like your atmosphere is there or kind of vacuum is there. So everything ultimately the thin film depends on what was the starting, has nothing to do what ends. So your substrate is plays a crucial part. The temperature of your substrate plays a crucial part. And if you are using some no, like environment also you are using, you are putting some oxygen or something. So all those things are ultimately deciding what is the kind of film you will be getting. What was, because your initial is nothing there, no? You are evaporating. So there is nothing like single crystal, no? Your starting material, you are evaporating it. So it is molten. So there is no question of having a single crystal or a polycrystalline material at the starting. Hmm? But there we are just evaporating it directly by passing the current through the material. But for all material, it is not possible. Generally, where there we have seen that material like metals we can evaporate. But when it comes to oxides and all, which has got very high melting point, or nitrides are there. So how to melt them? So in this case, we are using a beam of electron. So what we are doing, we have a cathode filament is there. So it is given high voltage and a electron beam is forming. So this beam is forming and there is a magnetic field. It's going inside this. So this electron beam will get diverted, and this is the material of which we want to evaporate, the source material. So we can have 1 cup or we can have 2 cup, and then this electron beam is falling on this. So because of the electron beam falling, so there will be localization, localized heating. And so it can be like oxide gets heated, so we can go to very high temperature. And because this material is going to very high, so they are water cooled, so there will be some water circulation inside. And then this full is kept inside the vacuum chamber. So we again have a vacuum chamber, everything goes inside. So rather than using uh, direct current in case of thermal evaporation, we are using a electron which is bombarding our material and it gets evaporated, and then the thin film is forming. The formation of the thin film, it remains the same, but the method of making the evaporating the material is different. So it is called electron beam heated evaporation source. So focus beam of electrons are used to locally heat the source. It can be used to heat or evaporate even very high melting point materials, and alloys can be deposited without dissociation. So if we have put alloy, or if we have got an oxide or nitride, etc., so they can be put here and then they can be molten. It can be made evaporate and form the thin film. And to make a multi-layer, we should have like 2 crucibles are there. So first the like electron beam is coming and hitting this. Then we change the magnetic field, the current to the magnet. This is an electromagnet. So that next time it is coming and falling here. So that way we can have a multi-layer deposition. So this is basically a photograph. So this is the vacuum system, and here we can see. So the electron gun is here. The filament is here. It comes out and then it falls on the. So material is kept here. This is a thickness monitor, and electrical supply is there, and the substrate is kept somewhere on the top. So it will get evaporated, and and the film will be formed on the top. So high intensity electron beam gun, so the intensity of the electron beam is around 3 to 20 keV. Is focused on the target material that is placed in a copper hearth. Copper, why it is copper? Because it has got good thermal conductivity, so it can be water cooled. Otherwise very high, so it will also start melting. So we don't want that. The electron beam is magnetically directed into the evaporant, which melts locally. No contamination comes from the crucible because or very small spot gets evaporated. Very high quality films can be formed. High deposition rate because there is lot of melting is there. Disadvantage is the process may induce X-ray damage because your electron Bremsstrahlung is can happen, and ion damage at the substrate because electron can collide with some gas, argon gas is there, so there may be some ion formation. At very high energies, the incident electron may cause X-ray emission, and deposition unit is more costly as compared to our thermal evaporation. So this is the two evaporation. Now feature is like this 270 bent electron gun is preferred. So the filament is out of direct exposure from the evaporated flux. So magnetic field can be used for beam focusing and scanning. Scanning means if we have got 2 crucibles, so we can scan. Sweeping of the evaporant source is useful for alloy larger evaporant surface area for higher deposition rate. Multiple pocket is preferred to allow sequential deposition of layers with a single pump down. Single pump down means once the vacuum is there, we can have sequential deposition of layers for the formation of multi layers. It is more complex but extremely versatile. You can achieve a temperature of around 3000 degrees. So generally you cannot evaporate any material way of very high temperature. So electron beam gun is there. So the crucible is kept in a silicon hearth. So sometimes we can put the material directly in the copper hearth, or we can put it in a like graphite boat or a alumina boat or alumina crucible, which is inside the, because we are not heating it directly. The electron beam is coming from top and heating it. The typical emission voltage is means the voltage to for the emission of the electron is around 8 to 10 kilovolts. So very high power supplies are required. The substrate gets exposed to secondary electron radiation can, and deposition rates are very high, but here also we can regulate by regulating the electron current, no? So it can be like 10 angstrom to 100 angstrom per second. Common evaporant materials like Al2O3, SiO, SiO2, SNO2, TiO2, so oxides are there, and everything a resistant heating evaporator will accommodate, huh? And other than that also, like we in the thermal evaporation we were talking about like gold, silver, tin, so low melting point material, so those also we can use here. But high melting point metals like nickel, platinum, no, iridium, rhodium, titanium, so these things also we can evaporate and make their thin films using the electron beam evaporation technique. So I will be ending my lecture here today now, and rest I will be completing on Wednesday. And before I go, I will repeat my question. Huh? So just slowly hear it. My question was gallium arsenide. Huh? GAAS. I have we have discussed the growth of gallium arsenide using the Zekrolsky technique. But normal Zekrolsky technique cannot be used for the growth of gallium arsenide. So my question is why? Why we cannot use the normal Zekrolsky technique for the growth of gallium arsenide? First question. And what is the changes we have made in the Zekrolsky growth for its Zekrolsky technique for its growth? Basically, if you can tell me that what is the problem with gallium arsenide, growth of gallium arsenide, and how gallium arsenide is grown. This is only two things, right? Everyone needs.
Also, আমাদের বিদ্যাসাগর সম্মাননা for his outstanding contribution and excellences in teaching and.
I'm not getting. What are you saying? I'm not getting outstanding contribution.
No, yes, ma'am. Yes. We are
Okay.
getting question.
Question is now clear.
Yes,
Question
yes.
is basically you have to tell me how gallium arsenide is grown by the Zekrolsky technique. And it is just two things. Huh? I just want that what is the problem with gallium arsenide and how we are overcoming that problem. And I just would request all of you that please don't go to ChatGPT and put this question and copy paste it. Rather than just think what we have learned today, it is very simple. What is the problem with gallium arsenide and how it has been overcome? That is only two-line answer, please send. Many people have given, but I could understand that a lot of ChatGPT has also worked for our answer. So that is not required. Let us not trouble ChatGPT. Very small answer is required from all of you. Whatever we have learned today, what is the problem with the growth of gallium arsenide and how it has been overcome? Just 2 points. Okay, everyone?
Ma'am,
Yes,
should
ma'am.
both the regions be written or only the main one?
Main. I don't want any elaborate answer or anything. Just
And
you
is
can just give me 2 lines. Gallium arsenide cannot be grown directly because so, and it has been, the growth has been done by using this as this. Okay. So
and
it is
ma'am,
fill in the blanks.
just one more question. Is the same book the Anthony R. West does reference for this module as well, or do we have a different reference book?
For the single crystal growth, if you want to go very deep, you can use Bryce and all, but you can carry on whatever you are reading. But if you just go through the module, whatever I am teaching here, That is enough for exam purpose, for the viva and all. But if you want to learn better into single crystal growth, I will share few books in the next. No, single crystal growth and semiconductor. For the semiconductor, I will suggest you can go to, you can start with our keytel only, the band structure and silicon and PN junction, all those things. And for the crystal growth, I can suggest, if you are interested, I will suggest a book next time if you want to go deeper. Okay.
Okay.
Any other question from anyone? Okay, then
Ma'am, videos are very nice. Actually, we got a clear picture for that.
yeah, that is the reason why I have put. So one was from my lab, and a few I tried to get it because generally at graduate, post graduation level, and even at research level, people are into thin films and all those things. But single crystal is a bit niche of an area. Many people are not working, so I thought you should have a flavor of it, how it is done and all, and how it is done in the industry, because this is a technique which is actually happening in the industry and coming to our house, their product. So that's why it was there. Thank you, you liked it. And you all have my email id, shash@brc.gov.in.
Yes.
If you have any problem or any suggestion, you can put it here also. Okay, thank you, have a good day, bye.
Thank you, ma'am.